Thank you guys so much for letting me remote in for the talk today. I appreciate that a lot. Um, and a bit of a disclaimer, this is a little bit different than my typical spiel in that this event hasn't quite happened yet, but I'm excited to talk with you guys about the brain-computer interface game jam and really sort of our goal here of promoting accessible game design for children with complex physical needs. So let's make sure that's going. Great. So first, going to talk a little bit overview, and I'll give a brief background on what a brain-computer interface is. Um, we'll talk a little bit about our motivation for the game jam, in particular how current BCI applications and paradigms are not engaging for kids, and really part of that is where your group will be able to hopefully help out. And then some of the goals that we have for the BCI Game Jam. In particular, how can we foster better brain-computer interface experiences? So a brief introduction to brain-computer interfaces, or BCI. Um, as a bit of a general overview, BCIs use specific recorded brain patterns to directly affect an environment. So these were originally created, originally designed for the idea of people who are completely locked in and totally physically impaired. So the traditional idea is for individuals who might have ALS, who have lost complete motor control of their body. And the question became, is there a way for us to use brain activity itself to bypass any sort of muscular control in order to be able to somehow activate and interact with the world? And the first instances were used with individuals who would look to communicate. So people who might have stroke later in life, how could we use a BCI to let them communicate if they're completely paralyzed, have no motor control, no way to speak or communicate? But this has recently been sort of expanded to things like motor rehabilitation, individuals who, after having stroke, can utilize these systems to activate the same neural pathways that they would using their afflicted limb without having to do the strenuous, painful actions of traditional therapies. And so really the main idea behind a BCI is we record the electric changes in the brain, and I'm going to be focusing on the non-invasive methods, also known as EEG or electroencephalography. In particular, this is a huge sticking point in that you might have heard other comments by people like Elon Musk lately in the news, where they're looking at more invasive methods. So that would require surgery and implanting something within the brain itself, which there's a lot of great work doing that in adults, but with the child population and the group that we're really keen on helping out, non-invasive is definitely the way to go. The next sort of key in this loop in this whole interface is the signal processing side. So looking at how patterns in the brain activity are processed in real time to look for specific features. This we'll dive into a little bit later, but the main idea is that specific activities will produce well-known patterns that we can then identify and define classes from. And so once we get these different classes, we can choose from these identified features and say, okay, when you were thinking about pattern A, when you were doing some well-known reaction, we can have that move the cursor left on the screen versus right on the screen. And then ultimately, you give that output back to the individual. So again, say you're using imagined movement, so you can pick up the differences between right hand imagined movement and left hand imagined movement, and that feedback can now be translated to moving a cursor left or right on the screen. So to dive a little bit more into each of these bits, electroencephalography uses electrodes on the scalp to record the changes in brain activity in a non-invasive way. So typically the neurons firing in clusters will give us a nice ability to say, okay, what is going on in the different general regions of the brain? Because it is on the scalp and it's non-invasively done, there is a little bit of a limitation in being able to pinpoint exactly where the activity originates. So anything that's happening deeper in the brain is a bit harder to pick up, but aspects that are right on the cortical surface, so things like imagined movement or attention, those are much, much more easily identified. Again, as this is a non-invasive method, it's useful for children. This can typically be used, or these electrodes can be applied with gel, or they could be dry electrodes, depending on what you see in this wonderful image. These are some gel electrodes completely covering the individual's head there. And really, the position of these electrodes allow us to be informed on the likely activity that's happening in the brain. So here you can see this CZ, C3, C4, hopefully. This is just a flattened down version, a common used image for EEG, where you have your nose in the front there, your ears on the two sides, and C3, CZ, and C4 are sort of the motor strip. So if you're thinking about imagined movement again, it's an easy one for everyone to picture. That's the area that will light up. And we can say, oh, great, they're thinking about that. If they're thinking about left hand movement, then C4 will light up. If they're thinking about right hand movement, then C3 lights up. Um, and it's just a nice, easy way for us to pick up this information. And then that recording actually becomes millisecond time series of information that we can then hunt through and analyze for the well-known patterns that we're interested in. So we're going to briefly cover the BCI signal processing aspect. Mind you, this is an entire talk on its own, an entire set of talks. So I'm just going to hit the main points here, but I'm glad to discuss in more detail as people are interested. So in BCI, you can really think about how to process these signals as two common types. There's asynchronous BCI, so this is where you are originating the brain activity and pattern yourself. So you yourself have imagined thoughts. So again, motor imagery is a common, easy one to pick up. And the EEG can be deciphered from that to say, oh, they were thinking about moving their feet versus their tongue, but it's all happening from yourself going towards the computer. And then there's synchronous BCI, which relies on an external stimulus to be able to get your brain to have a well-known and well-defined response. Two of the typical ones that are talked about are the P300 or the positive 300 response, which is really what we're going to be looking to use in our game jam, and something called a steady state visual evoked potential. Both of these rely on the visual system to give a stimulus that we can then pick up in the back of the brain and say, oh, hey, they were focused on this on the screen versus something else. So a typical processing pipeline is you have your EEG signals and you need to pre-process them. So remove artifacts like movement and blink and noise and distraction. And then you have some sort of feature identification or extraction. So on the side here, you can see I have a nice little P300 example where you have 4 different hexagons. One of them is lit up. And if you randomly light these up, you get the well-defined P300 response, which basically means that if you're staring at something and you're paying attention, like at my screen on the brain right there, and something randomly flashes, then your brain says, oh, hey, what was that? And it gets very excited about this new unexpected information. And it gives you these nice peaks over specific areas that we can say, oh, great, they were focused on this or that. So in this case, we'd be able to tell if they were looking at the bottom left and it lit up, oh yes, that's what they were focused on. And that then allows us to classify. So we can say, okay, we're looking at a target, which is whichever hexagon lights up. That's the one that they're paying attention to versus non-target. So we can then say, oh, yep, every time this bottom left one lit up, that's the one that they wanted to select. And there's really a whole bunch of approaches for this analysis, again, beyond the scope of here, but I figured it's worth talking about. The classic machine learning approaches, deep learning, neural nets, those are all very popular. Something called independent component analysis you might run across a lot. That's just to help de-noise and pick out specific features, multi-way analysis, etc. And I think really of importance to the group here is there's a lot of available BCI software packages that you can get up and running with this pretty quickly. So I'm going to list a couple, but it's definitely worth recognizing a lot of these have built-in aspects for you to start processing EEG data and building your own BCI loop pretty quickly. So there's things like BCI 2000, which is a C-based program, but it's very well maintained. It's by a group out in New York. It's very commonly used, has everything you could think of. If you work in MATLAB at all, I know that's a curse word to some people, but EEG Lab, BCI Lab, and Field Trip are all really great MATLAB programs that, again, have everything built in. You just need to know how to call them. In the Python world, you have NeuroPipe and MNE, which are both very accessible. NeuroPipe has a very easy to use visual coding aspect to it. MNE is a bit more classically command line coding, but both of them work very well. So let's talk just a moment about the BCI stimulus and feedback as well. It's important to understand that the stimulus to elicit these sort of synchronous reactions needs to be well characterized and well understood. So I can't just show like 6 pictures of dogs and say, okay, think of your favorite dog, and be able to expect to get something out. There has to be a physiological basis to the stimulus that you're giving for us to be able to pick it up from the viewpoint of the EEG recording and say, oh yes, this is what they were looking at. But really, as long as you're within the realm of those stimulus, you can provide a lot of different types of feedback in order to get that stimulus to be supported or elicited. So, for instance, if we're talking about the P300 again, I mentioned this visual example, which you see on the screen, but you can use auditory stimulus or tactile stimulus even. So vibrations on wrists or feet and whatnot, and have the individuals pay attention to those and get the same response from the P300. So there's a lot of ways to integrate in these stimulus presentations through different mediums. And really the importance here of the stimulus is that this is what completes the loop in the BCI from the brain recording and the signal extraction, so that there's actually something that happens. So without that loop and that feedback of the little check mark there, you end up losing a lot of useful information. And that's really a key area that needs more attention, particularly with these applications for kids, as you'll see in just a moment. And I think that's where it's your guys' time to shine, in that this whole idea of how to provide the feedback and the engagement, the visualization, in what manners to effectively do that while maintaining the physiological integrity needed to get the proper outputs, the proper stimulus to the brain, is a open question, and one that I think really should be focused on more as BCI develops. So quick review now, since you guys are all BCI experts. BCI is used to directly influence the environment via brain patterns. You have this lovely colored EEG on the left. Activity can be self-initiated, asynchronous, or from an outside stimulus, synchronous BCI. And really, you want to identify and extract certain features from this EEG, from this recorded brain activity, so P300 activation, and give that output from some binary or higher classification to the computer. So we're going to shift into a bit of the motivation behind the game jam and look at what is currently state-of-the-art BCI applications, and hopefully how to adapt these for children, or the lack thereof of adapting them for kids using this. But first, why are we interested in adapting BCI for kids? We actually are one of the few labs in the world that's working on BCI for kids. We work with children who are severely physically impaired, but cognitively are doing very well. So they might have had some sort of early life insult or trauma, like pediatric stroke, or rare brain diseases, which leave them unable to communicate or physically move their bodies. And so really, children have quite robust brains and they're still capable of significant change. And BCI is kind of a great way to promote healthy change within those kids. And if you can move them just up a little bit as their brain is still so flexible compared to an adult, then that allows you to be able to get these really great, wonderful outcomes later on in life that are 2 to 3 or 4 times higher than what you'd expect from intervention in adults. And really, they're an ideal population for long-term BCI use in that using this technology, the more that you use it, the better you become at it, and the more capable you are of doing that. And in adults, there's a lot of limitations in terms of who's administering it, who's helping out, having full-time carers, etc. Where with children in these situations, that's all very much built in, and they are still very keen to be learning these things and interacting with their world in a nice, exciting manner. But there's quite a few challenges. First, it's very difficult to extract useful EEG information from the kids. There's a lot of movement that's happening because typically they're quite bored. There's a lot of variability in the features that we're extracting. Again, things like attention make a huge difference in the amount of noise that's coming out of the EEG. And really, a majority of these applications that have been developed are aimed at adults. So to really nail that point home, uh, when you think about communication in BCI, it's just spelling everywhere. And all people are doing over and over again, these are the actual user interfaces that come up full screen for an individual. And they just repeat different variations of spelling, which if you have me who's an adult and have me sit down and watch these different letters flash either rows at a time or boxes at a time and sit completely quiet for 10 seconds in order to select a single letter to try and spell something out, I get extremely bored, let alone if you bring in one of our 7 or 8-year-old participants. They will not be interested at all. And again, this is the type of feedback. These are actually good examples of exciting feedback that you get in the spelling world, but that's basically it for the communication side. And there was actually a really good um, paper from Norton et al. Last year. We had a great chat, and they were looking at BCI in children and how to make it more engaging. And in this case, they were using just a pointed arrow and had the kids try and focus on one of those 3 objects. And this is an example of the original interface. I couldn't get the gamified one, but they switched it and found a huge improvement when they switched from just having these circles and asking for this basic feedback to having exciting images, having them select like the rainstorm or the sun and something that had a bit more of a story to it. And the kids did much better there. And that was for 9 to 11-year-olds. Again, I mentioned a bit about motor rehabilitation at the beginning. This relies on your asynchronous BCI, but I want to call to attention here that it's pretty much the same aspect every time, which is you prime the user attention by saying, hey, look at the screen, look at this plus, and then you present some target for them to try and imagine moving a cursor towards. So this is a very early paper on using motor imagery to have a cursor back, but this is the kind of feedback that we're trying to give children again, where you say, okay, imagine moving your right hand and we're going to push that cursor to the right, and that's great for maybe 1 or 2 trials, but it becomes quite dull after a solid 50 trials of this, and it's just limited feedback. Another good example here is from Fabien Lott's group over in INRIA in France. Again, they do some really great work. They're looking at how to improve affected limbs, but the feedback is basically imagine your left hand here, and the more they imagine it, the bigger that blue bar gets, and that's it. That's the whole feedback that you're presented. So to recap some of the current limitations of BCI applications, these are, as you can see, kind of aimed at answering research questions. So they're very focused on saying, okay, can we do this thing to prove that it works for maybe 2 sessions over 2 days, 50 different trials. And that really then leads to a lot of limited appeal for young users, as they're very spelling focused, they're very utility focused, which are critical and important as BCI is still in its infant stages, but it's still quite challenging to motivate the kids and have them be excited. And really, that part of that problem is that there's not a focus on sustained use of the BCI technology. Um, and again, this goes to if you have patients coming in who are adults or you're trying to answer a research question, they are there for maybe a couple weeks or months. We have some participants in our lab who have been coming in once a week for nearly 2 years now. So it's very important to have things that keep them engaged. There's only so many times I can try and get them to use the speller, or one of my colleagues can get them to use the speller without them being frustrated that it's sort of just like a continuation of school, but a very slow, frustrating school. And really, when you have this feedback, which is dull, and these sessions, which are long, you end up with people who just aren't quite paying attention. It's how you end up with bored kids. So that brings us to the BCI Game Jam and how we're hoping to sort of promote these better BCI applications with some multidisciplinary collaborations. Um, as a bit of a overview, there have been some work done in BCI and gaming. We're not the first people to think of this. Again, this is mainly focused on adults, but just some classic examples. On the left here, this is a very classic one of a group out of Graz, Austria, in which they used a BCI overlay so that an individual could play World of Warcraft on screen. Unfortunately, the downside being there were only 3 inputs that they could do, and World of Warcraft has quite a few more than that. So they were overlaying this BCI as another way to control the game. Or on the right here, this is from a group in the Netherlands called Mind Effect. You can see that they are using 2 players here to play Pong. And I bring up these 2 examples because they sort of give great prototypical examples of what right now is happening in BCI and gaming. You either have games which were not designed with BCI input in mind, like you have on the left, in which there's a lot of restrictions there occurring and not a lot of ways for the BCI controller to actually be used, but it's a full-fledged game and it's quite fun. Or you have what's happening on the right, which is a very basic game, which is fun, but something that's made from individuals who are more focused on the BCI side and just build something very small, very easy, that they don't really have to think about long-term engagement. And that's where we're trying to bridge these two to try and get some feedback from groups to have maybe a better view of gaming. So our goals here is we want to reach out to the game developers and the enthusiasts to first raise awareness of BCI technology and hopefully have them help in terms of improving the BCI user experience. And ideally give them some hands-on experience in using BCI technology as a input schemes so that they're aware of some of the limitations like delays and whatnot that are not common with other types of input um, in games. And really, we're hoping then to promote some accessibility in the game design and game development. And ideally, again, trying to say, hey, when you're developing this game, how can you think about accessibility as one of the key cornerstones here? And how could you perhaps integrate in some of these alternative interaction schemes so that you have a game that is completely functional on its own? You can access all parts of it using something like BCI, which is sometimes a bit slower, has limited numbers of inputs, etc. And part of how we're hoping to promote this in the game jam itself is we're going to have a couple of panels in the jam, including a family panel. So these are actual individuals and their family who use our BCI systems who come in, as well as a BCI expert panel, which we're quite excited about. And we've also developed a tool for easy integration of the BCI, in particular that P300 response into Unity. And I'll show a couple of slides at the end here about that. And our goal is to improve the limited library of child-friendly applications available. And so we're hoping that with the better visualization and engagement, this higher amount of entertainment will lead to more sustained use of BCI, which the research has shown if people are engaged, they will use it more. So just a few shameless self-promotions on the Unity asset tool. So I had a summer student over the summer who helped out and created this easy to include asset for Unity, which does the P300. So it's going to start over on the right. You'll get some flashing cubes. The idea being that if you focus on any one of these given cubes, then it'll elicit that P300 response as long as you're focused on that. What's nice about this asset is it's quite flexible. You can change the flashing properties, the arrangement of these cubes, other objects. As you can see here, we're now doing rows and columns flashing rather than single ones. And really, it takes care of all the back-end BCI required information. It uses something called lab streaming layer to send and receive the inputs. But it has all the necessary codes for interfacing with the signal processing software of your choice, as long as it's using lab streaming layer of some sort, or even as long as it can process EEG. But that's all included in this. Here is my very fun examples of how to use it in Unity. In here, you have a game objects, which can be selectable, or as my summer student did, he made it into a user interface. So instead, you can click on those and it'll push the ball back, which is quite nice. This was my poor example here. You select a square and then it'll either pop up Mario or a classic Minesweeper thing. But if you're interested, please come and join us for the game jam. We're quite excited. It's November 8th through the 10th. It's open to anyone. We will be distributing the tool. And that, I want to say thanks. Thanks to the children and families who make this game jam worthwhile. And then to all of our sponsors, particularly I want to thank my supervisor, Adam Curran, who's doing a great job helping me support this, as well as the other people in the BCI lab team, the Data Visualization Center in University of Wyoming, and the CAB for having me today. Excellent. Any questions?
Great, thank you, Eli. I have a quick question while other people are raising their hands. You said the asset's available. Is it available on the Unity store, or is it like on a GitHub site?
Yeah, it's on GitHub. I'm going to be releasing it. So I finished it and verified with the next speaker, actually, who will be talking with you, Kyle. We did some test runs, and so I'm going to be uploading it today, hopefully. So you guys are actually the first to get to see a preview of it outside of my lab here, which is great.
Eli, thanks for the presentation. Couple questions. You showed a lot of 2D examples. Have you looked at any kind of gaming in 3D or simulated environments and the head-mounted displays? One, and two, what are the limitations on the complexity of the scene that's possible in that kind of environment with the BCI?
Okay, so just, sorry, it was a bit hard to hear, but your first question asked about 2D examples versus 3D examples, I believe.
Correct.
So yeah, so a lot of people have integrated this into 3D environments. In the 3D environments, there have been some gaming examples. I can maybe share an example of that if we get a chance. But you can have a VR headset overlaying. You can also do an augmented reality headset overlaying. In both cases, though, typically in the VR headset, this is used for something like rehabilitation again, where they will just have two animated avatar hands that are lifting up or down. And actually, one of our current innovation pitches that we're trying to do is make that more exciting for kids. And the whole P300 Unity asset, the reason why it came up is we've been looking to integrate it into the HoloLens and the virtual environment, but there was quite a bit of issue in synchronizing some of the other softwares, because you have to have a nice synchronization between your stimulus and the AR with what's happening in the EEG for it to work effectively. And that's where this whole idea of using Unity as compared to some of the commercially available ones, which weren't syncing very well, came up, and why we sort of developed this whole thing. And then your second question was?
Really just about the complexity of the scene. When you showed two examples, one which was the World of Warcraft example, which suggests a pretty complex scene, but you said it had limitations
Right.
in terms of how it was possible to interact with using BCI modalities. So then, but the other example, the Pong example, is pretty simple, right? I mean, it's really a lot of complexity. So is there a balance that you're looking for between the two of those, or what are some of the limitations in terms of the scenes and how it would stimulate the visual cortex in this case, and the interaction with the user?
Gotcha. Yeah. So so there, it depends on the paradigm that you're using and the way that you're trying to integrate in the BCI. So on the left here, what you're actually seeing is they're using an asynchronous BCI, where this individual is imagining left hand, right hand, or feet to do. They've mapped onto 3 keys in the World of Warcraft example. You can actually look this up on YouTube and you'll see it. The issue there being that it's a bit hard to have consistent outputs, so they can do 3 buttons, but sometimes it's a bit difficult. And mind you, this person is a typical developing adult individual, so this will work very well for them. On the right hand side, this is a synchronous BCI that you're seeing. So you have these different flashing lights on the sides here, and that'll move your paddle up and down. And so the complexity is still quite an issue in that, at least for children and for non-invasive BCI, you could most likely get 1 or 2 reliable asynchronous movements out, likely 2. And you can get, depending, more synchronous BCI inputs, because your classification scheme is going to be target versus non-target. So if you imagine this here on the right, a bunch of different options, say 1 through 6, you are always doing the same classification, but you have 6 option outputs that you can get. So as long as they're focused on the top one, then you can say, okay, yeah, they wanted to go there. And so that gives you more degrees of freedom, but it's a bit more challenging in the sense that you have to synchronize specifically with those different options, and you have to make sure that these options have a good, healthy way to view it. Does that make sense?
Great. All right. Thank you, Eli. I don't see any other questions, so thank you again.
Yep. Thank you.
And as Eli mentioned,